On the panel today, of course, we have Jennifer Richter, partner at Akin Gump, working on the communication solutions for UAS and automated air taxis. We also have Dr. Badri Younes, who is the NASA's Deputy Associate Administrator for Space Communications and Navigation, commonly known as SCAN. We also have Dr. Parimal Kopardekar, who is the Director of NASA's Aeronautics Research Institute at NASA Ames and a Senior Advisor for UTM, UAS, and UAM for NASA Aeronautics. And we also have Paul Nelson, who is the Integration Manager for Cybersecurity and Communications at NASA Glenn Research Center here with us. So what I would like to do is, first of all, set a stage in terms of the future challenges that we have on how we see airspace evolving. And for that, I had a couple of slides to show. Let's see, I just want to see if the slides are up and available. And in terms of, let's see, I'm not seeing any slides on my screen.
Akbar, so hopefully you will not see the slides.
Is. So the first slide that you see, it's essentially showing what the future airspace construct will look like. If you were to look at the current traditional airspace, it's primarily right now occupied by your standard tube and wing body aircraft, both in terms of the commercial transports, in terms of the airliners, and then general aviation aircraft. And of course, in the current aviation, we're also seeing UASs beginning to occupy both the high altitude airspace as well as the lower altitude airspace in terms of the smalls below 400 feet. However, if you look at this picture, looking in the future, the airspace is going to be far more complex. The diversity of users is going to be far more higher in terms of the variety of users occupying, not only in terms of vehicles, but also the type of missions they'll be flying. In the higher altitude airspace, along with your commercial transports, even there, the variety of aircraft will change. You can start seeing supersonic aircraft. You can start seeing more electrified aircraft, such as the NASA's truss-braced wing concepts and various other vehicles occupying that airspace, as well as highly automated freighters and UASs. And in the lower altitude airspace, you start seeing vehicles for urban air mobility that are currently in a great deal of research and initial production by a lot of the industrial partners. And of course, if you go to these really low altitudes of below 400 feet, you start seeing a lot of small UASs for a lot of missions. It could be from package delivery to inspections to photography to in the applications of those smalls. It's countless for me to even to mention in terms of the variety of use cases. Even in the traditional air transport operations, you start seeing a lot of the variety of uses to be coming into play. So this airspace also provides us a challenge in terms of volume. If we look at the current types of operations, we have about maybe 50 to 55,000 operations a day in the current national airspace. However, looking at this future, the operations will be in the millions of operations. If you start counting the small UASs and also the urban air mobility, the automated freighters, space access, and everything else, and even the ultra high altitudes that operate high endurance vehicles. So therefore, in order to be able to effectively manage the operations of all these vehicles, we'll need to start looking at different constructs for COM and NAV in order to effectively provide services to these systems. Now, if you go to the next slide, in here you see the way we see the evolution of the airspace, going from the past to present to the near term, and then sort of the 2035 vision that FAA has developed and NASA is jointly working with them, and even beyond that into the 2045 concept. And as you can see here, we start seeing the variety of the evolution of the way we manage airspace. We're sort of going to be going more into the adaptation of machine learning AI algorithms towards a very service-oriented architecture to provide services to users. So this is what's upon us, and this is the context we'll be having a good discussion today on how do you effectively provide the comm and nav services to both the variety and diversity of use cases, as well as the sort of the spectrum of an evolution of the way the airspace will be managed in terms of 2035 and 2045. So with that said, what I would like to turn to now is our first panelist, Jennifer Richter, to provide her thoughts on, up till now, what are all the challenges that they have seen in terms of technical challenges they have seen in regards to her sector that she represents, as well as how we have addressed all those challenges up to this point. Jennifer?
Great, thank you very much. So yeah, as was just alluded to, I work actively with the communications industry, and I sort of sit between the aviation industry and the communications industry in trying to determine a multitude of questions related to CNS for all of these new kinds of advanced aircraft. Where we've been over the past 7 years or so has been just trying to convince the regulators and industry that new kinds of spectrum resources and network resources could be used to satisfy the communications needs of low altitude UAS. Now, of course, those questions are relevant to a whole stack of aircraft all the way up to the stratosphere, but we really started with just looking at the low altitude UAS. And the question was, what kind of spectrum resources are suitable? Should we be using unlicensed spectrum? Should we be using commercial wireless spectrum, satellite spectrum? Or do we need to rely on the traditional aviation resources that always have been used to support aeronautical use? Related to that is how that spectrum would be deployed in order to serve this new market. So many of these spectrum resources and networks were built with terrestrial communications in mind. But if we want to use that spectrum both on the ground and in the air simultaneously, what kinds of network optimizations might be necessary? So what makes this conversation really complicated, what's made it complicated to this point, and I suspect this will continue to be true, is that we have a couple of different regulators that are involved in these discussions. So we have the Federal Communications Commission, who governs the use of spectrum and is generally looking at technology coexistence and keeping operations interference free. And we have, of course, the Federal Aviation Administration, whose primary mission is safety. And taking a look at these spectrum resources from those two different points of view, which don't always arrive at the same endpoint and conclusion. So we've had a series of discussions over the last 7 years with these two regulators, and I think we've come to a really good point. I think, and the remote ID NPRM really evidenced this. I think we have gotten to a moment here where at least our aviation regulators are recognizing that there isn't to satisfy the communications needs of all these new aircraft that will be flying, and that we need to be relying on other kinds of spectrum resources, the commercial wireless networks, the commercial satellite networks. This seems to be a necessity, not only for low altitude UAS, but for the small to medium UAS, advanced air mobility, the thin and short haul, the large UAS at HAIL. We're going to have to rely on a combination of spectrum resources and networks. But how do we satisfy ourselves that these networks and spectrum resources can be used in the air without causing interference to current uses of these networks and resources on the ground? These really are the essential questions. And beyond domestically and satisfying the questions of the FCC and the FAA, how do we convince ICAO that they too should view these commercial resources as safe and viable? So where we've arrived at after these 7 years of discussion with regulators is that the United States, at least, and a number of other countries are accepting that the aviation industry will need to rely on these other kinds of spectrum resources, commercial wireless networks, satellite networks, but that they will have to interoperate with aviation spectrum, because not all of these use cases that you've just gone through can be satisfied with those resources. The aviation networks will have to be used for a number of these kinds of operations. And so how do we interoperate with all of these different resources and networks? So the challenge for our regulators now is to confirm that these commercial resources can in fact be used in a manner that's safe and interference-free, and that brings us to the work that lies ahead and the contributions that NASA can make, which I'll discuss later on in our panel.
All right, thank you very much, Jennifer, for your perspectives. Next, I would like to turn to Dr. Younes in terms of your perspectives on, especially with your program, because I mean, to be blunt, you're literally moving packets of data into the middle of the galaxy, and being able to do that both safely, reliably, and securely, I'm sure is a huge challenge. So we'd like to hear from you in regards to your perspectives of you know, the technical challenges that you've been able to address through your program, and also how you see that evolving towards the future construct.
Well, thank you, Akbar, and definitely, I have a couple of charts. I don't know whether they are on the screen or not. Can I get a word that they are being displayed? Because I have no way to see.
Yep, charts are up, Badri.
Okay, great. Definitely, Jennifer touched on it, interoperability. And if we look at our domain of operation, spanning from anywhere, you know, from the ground, the surface of the Earth, all the way to deep space, well beyond the solar system. We have missions that have crisscrossed the boundaries of our solar system, and they are now in the interstellar area. We have a lot of activities taking place, both in the near-Earth domain as well as in the deep space domain. In the near-Earth domain, NASA has been asked to help to work with the commercial industry to commercialize space. At the same time, we see at the suborbital level commercialization of suborbital activities and proliferation of UAVs and a lot of aeronautical kind of capabilities. Near the moon, we have a major effort to land the first woman on the surface of the moon by 2024, and the next male astronaut there too. And from there to begin our journey to deep space, hopefully to Mars and beyond. The operational environment is going to get very complicated. So we are working very closely with the industry and as well as other government agencies to push for an interoperable space, both on the common nav level, that can leverage all the civil and commercial as capabilities, both domestic and international, to enable the seamless transfer of information. Imagine that, having this interoperable environment that can pull resources and capabilities from everywhere. But we know the capabilities are distinct one from the other. So how do you push interoperability among all of these systems? Every provider operates at a different frequency level from the others. They use different waveforms. Some providers are the waveforms. That's all of their. The waveform is their business. How do you bring this about? How do you overcome the spectrum issue, this regulatory issue? To go through to challenge the COM Act of 1934, it's a major challenge. To push anything into the regulatory environment is an impossibility. We are trying to do that. We pushed for an item on the agenda for 2023 to allow for space-to-space kind of authorization for some of these FSS providers to support space-based users, and hopefully we'll be successful. We tried to get the authorization for the MSS. We were not successful. We believe all of these challenges can be resolved through technology. Technology is the key to enable us to ride over the regulatory choppy waves and to provide a robust service to our users such that they can roam in space. Definitely roaming in space, that's an idea that we've been targeting, pushing for quite some time, to allow our user to go from one system to the other unimpeded by the technical and the regulatory challenges. And we are pushing for autonomous operation in space and autonomous navigation. As space gets more populated and the population density starts to go up, we can no longer schedule the support on a user-by-user basis. You really need to rely on the mission itself and the platform itself to negotiate with the provider and negotiate access to be able to reconfigure themselves to get that support. So we really need to have a collaborative environment among all of the key players. So on the next slide, we show some of the key ingredients for an interoperable space. Definitely you need to push for common standards. Our space industry has been relying on CCSDS, the Consultative Committee for Space Data Standards. We started to look at the commercial standard and trying to see how we can bridge the two. So we are pushing for the kind of technology and standards that are suitable for optical communication as well as RF communications. We are looking at the 5G and trying to see to adapt 5G and potentially 6G and 7G into our operation. The spectrum, we are working across all of the spectrum domain. And I understand spectrum. I used to be the director of spectrum management for the Department of Defense back in the glory days. What we could accomplish there. So and we negotiated many win-win solutions, and I believe in order to approach the regulatory framework, you really need to have win-wins, because you not need to look only for your own interest, but to have the collective interest of the entire industry, both government and non-government. I have been pushing for quite some time for the spatial and the temporal aspect of spectrum. How can we maximize the availability of virtual spectrum from the 6% now, which is, if you are to measure the utilization of spectrum, it's about 6% at one place at any point in time. I'd like to take it to the 80 and the 90%. Technology will allow that. And the technology, we are investing in, in low TRL, as well as we are really pushing some of the high TRL technology readiness level. So we are trying to push technology such that by 2024, we can have the kind of receivers that are multilingual, that can talk to any, and these will be hosted on our spacecrafts, will be able to talk to any network. They will be able to reconfigure themselves to operate, with any waveform at any frequency. So we are pushing for these multilingual receivers, and we are pushing for also the cognitive technology that can ride on this, that can provide for proper routing, proper management of resources, communicating with any platform, and be able to enable the smooth transfer of information between any 2 points. You need that collaborative environment such that the node at any time will know the status of the network, what channel is busy, what channel is not busy, and be able to adapt in real time. And we are relying on the cognitive technology because you want the machine to learn on its own based on its experience, to allow it to make decision on how to what service and what waveform to use in the future. So in addition to the cognitive technology and also the wideband receiver, we are pushing for a multi-GNSS receiver. Autonomous navigation is so critical. It can reduce the burden on all of our networks and will allow the instantaneous position, navigation, and timing solution to be available to the spacecraft. These are the kind of technologies that we are pushing. We expect some demonstration to take place between now and 24. NASA is no longer building its own satellite, data-related satellites. We are going to rely on the commercial industry. There are plenty of them, and we see the technology we are doing, the interoperable space, as our key, as key to enable this robust roaming in space. Thank you.
Okay. Thank you, Badri, for that really in-depth perspective on not only your past capabilities, but the way you see the evolution into this very multi-partnered approach going into the future on how industry and government can help address the common challenges going forward. Really appreciate that. We'd like to now turn to Dr. Kopardekar to provide some perspectives in regards to how, from NASA's perspective, the research that's been done in aviation, some of the technical challenges that we've addressed and have looked up to now for, enabling UTM operations, because I'm pretty sure you all know him very much as the inventor behind UTM. So in regards to how we have addressed UTM, enabled urban air mobility, UAS, and of course now looking at more highly automated aircraft such as highly automated freighters and various other concepts. PK?
Yeah, thank you. Hopefully everyone can hear me. Great to be here. And originally when this was going to be at Case Western as a in-person meeting, my daughter was really excited. She said, I will travel with you, even though it was a summertime, because that's where she goes to school. She said, I'll come with you to Case Western and show you around the college. But unfortunately, she was a little disappointed, but maybe next year. So I'm very much thankful, Akbar, for inviting me. And it's a great honor to be part of the Glenn Symposium. This is a really great event. And I write nice memory and in honor of the real true American hero. So thank you, Badri and Jennifer and Akbar, for setting the right stage that I can just expand on a few things that have been done. So as we start to look at the airspace operations and air traffic management and associated safety, we started off right now with 50,000 operations. That at a time there are 5,000 to 7,000 aircraft in the sky, and the communication goes from air traffic controller to pilot, and also from cockpit to the dispatch. As you start to scale this and say, how can I enable millions of these drones and urban air mobility operations and high altitude platforms along with the manned aviation, we start to look at what are the challenges or barriers, or where do we need extreme flexibility. We realize that human workload is one of the challenges. The second challenge becomes then the communication. If the human workload, to elevate human workload, we put more automation or decision support tools or autonomy. Once we realize that we put more automation and autonomy, that needs to be communicated and connected with across all the assets, all the aircraft with each other, aircraft with ground, and aircraft with their dispatch or network operations center. So now you're looking at this completely different architecture that connects these pieces, as Akbar showed in 2035 and 45 vision. You have a cooperative traffic management. The cooperative traffic management only works if everybody has all the information about the current situation in the airspace and the constraints and where the other objects are, other aircraft are, so you can stay away from them. Currently, that information is only available in air traffic control and air traffic controller. So fundamentally, we start to unleash the capacity, and one of the linchpins for unleashing the capacity would be this communication network. How do we actually enable automated systems who have all the information that is necessary to plan and replan and dynamically change their routes once they are in the air? So that requires a nicely integrated communication. If you're looking at urban air mobility, you need to have vertipad information connected to the network operations center, connected to basically the aircraft, urban air capable aircraft. And once you start to connect and you say, okay, this will work, then you say, where are the challenges? Then spectrum issues come into the play, the frequency issues come into the play, congestion, frequency hopping, and things like that really become very important. And then all of a sudden you realize, wait, the current patchwork of communication may or may not be the best way to go about moving forward. we may have to look at aviation network as a new kind of entity, that one that's more secure than today, one that's more scalable. It's multi-band, multi-spectrum, multi-frequency, dynamic allocation automatically based on what's available and such. We cannot afford to have spectrum as a bottleneck to enable the scalability. So that's fundamental promise, is to figure out how we can architect basically architect this communication, navigation, surveillance system that will enable us to scale with and have this connectivity, extreme connectivity that's needed with the ultra high bandwidth, so that there is the awareness of what's happening in the airspace all the time with each other and to the regulatory entities. So we learned a number of things in UTM, as Akbar mentioned, it's unmanned aircraft system traffic management. So we started with 500 feet and below, when drones are working together in the airspace and there are multiple drones operating, their operators need to know the information about each other's presence. Their operators need to know about each other's intent. So there's a communication that happens there. And then if there are any dynamic events, such as there's a public safety priority or search and rescue that comes in, then you need to send information to these operators and operators to drones saying that, we need to clear the airspace, there is an emergency here. So those things require new way of thinking and basically agile communication schemes along the way. Now, if you have a number of aircraft that are operating in a pocket of airspace that's managed through current system, then they have very tight basically allocation of frequency, and you change frequency as you move in the airspace. Similar setup needs to happen, but that needs to happen very dynamically inside the airspace if you have scaling. The current basically procedures is pilot and controllers talk to each other, controller assign a different frequency as they move from one airspace. So that kind of a voice communication is no longer practical when you have millions of vehicles in the sky. So that needs to happen very elegantly and automatically along the way. The other part of that is we learned is V2V communication, just like we basically see in the car industry. We need to have the vehicle-to-vehicle communication once the vehicles are aircraft are in the air, so that they can share each other's intent with each other and stay away from each other. And in case of conflict, they can cooperatively decide what's the right thing to do. Those V2V standards need to be built for airborne platforms. Those V2V standards are critical because once scalability is there, one of the fundamental workload factors is the conflict detection and resolution and the communication that's related between pilot and controller to resolve those conflicts. So if we have V2V, you could see how we can unleash the capacity logjams that exist today. We learned that through a series of tests that we did towards unmanned aircraft system traffic management capability levels all the way to the urban airspace. We have some challenges in the urban airspace. Sometimes the frequency gets constrained. Sometimes you have calls dropped. We see that Zoom calls getting dropped all the time. So how do you make sure that there is a persistent aviation grade quality that's needed to support these operations? So you try to scale that and say, okay, how do I go from small drones to larger drones to entire manned aviation and upper airspace, as well as all the way to the space traffic management, as Badri mentioned before. So we have a number of these things, and the patchwork that currently occurs is not the best way to look at it. So when we start to look at the vision of 2045, we need to start to look at what is the right platform and architecture for the communication, navigation, surveillance, one that is, again, summarizing multi-band, multi-spectrum, dynamic allocation, automated to support the scaling of these operations in real time. So there is a real-time system-wide safety issues. So we have an effort in Akbar's program, in-time system-wide safety assurance. So in order to do in-time system-wide safety assurance, the connectivity is crucial. I'll give one example and I'll stop here. So as we are moving towards urban air mobility, let's imagine that you're flying eVTOL and there is a bird strike. We have seen a famous bird strike example in New York and Hudson. So that could happen. If that happens, you are in a position to say, I need to decide what to do. Connectivity becomes very important at that stage. You are at the critical stage. You need to make quick decisions. You need to figure out which vertipad I should go and land. When you try to figure out which vertipad I should go and land, not only you're worrying about who else is out there in the sky, but you are also worrying about, is that vertipad available? I need to know that information. Is the weather near that vertipad is clean? I need to get that information. I need to know that there is a maintenance crew, or there is a way to get off that ramp, or there is someone else occupying that, or how do I communicate to someone that, hey, there is an emergency, please give me a right of the way here. So all these things are practical, but we need a good, reliable, consistent, resilient communication to enable these contingencies that could perhaps happen in the future. As we start to depend more and more on automation to take care of scalability issues, then we need more and more reliable communication to address and support management of these operations and the scale, particularly under off-nominal conditions. And that's why the main message here is we need to look at the architecture of the CNS to enable the future scalability under nominal and off-nominal conditions. And it's very much critical aspect towards getting to that vision that Akbar mentioned for 2045, where we will have diversity, density, and tremendous digitization that will occur. Thank you, and back to you, Akbar.
Okay, thank you, PK, for that great perspective of where we've been and in terms of the challenges that's facing us going into the future. We'd like to now turn to Mr. Paul Nelson. So, I mean, if we look at the evolution of the way airspace is going, security is going to be a huge aspect of it. It has been a big challenge and a big issue for us to address up to the past. However, if we look at the past systems, even if a lot of the FAA systems, they were, not connected to the world. They were either systems are connected by wire, so you can do a lot of the physical security in order to maintain the system integrity. However, if we go to more digital, cloud-based, and also this very distributed architecture that Dr. Kopardekar and Dr. Younes described, as well as the future challenges that Jennifer described, the security of this very distributed environment is going to be critical. So we'd like to hear about your thoughts and perspective, the challenges that we need to address in order to enable the safe and secure operation of this very distributed environment.
Thanks, Akbar, and thanks to the AAS for the invitation to speak here. So, as noted earlier, I'm the integration manager for cybersecurity and communications at the Glenn Research Center. I have the same role for Akbar within the Airspace Operations and Safety Program. Glenn is the competency center for communication technology research for NASA. I've worked in the SCAN program under Badri as well over the years. There's a few things that we have to look at when we start to talk about security, and unfortunately when we talk about communications and security, what we're doing is having a complete linkage between the two. So we have to talk about how the current NAS communications environment works, where we have to take that communications environment for the future, and then how do we start to address security as we do that. So kind of the current state of the National Airspace Communications environment is a single-use spectrum environment in which we've designated individual spectrum for individual usage. So for instance, ADSB has its own spectrum, nobody else can use it. What we're running into, and this goes back to PK's comments on how we have to start integrating, we're running into fundamental spectrum limitations for aviation spectrum right now. We're not making more, so we have to find ways to do it more efficiently. So overall, this creates a barrier to new concepts and new technology entrants. That coupled with a fundamental regulatory issue we have, and that is that the functionality of safety critical systems is assured by bearing off isolated spectrum. You can look at ADS-B as an example. The spectrum there is intended to make the detect and avoid piece as responsive as possible by not allowing anybody else to use it. So we've got this isolated safety critical spectrum issue that's regulatory on top of it. So we have to look at those as our starting points coming into this. In addition to this, we have the current security of communication in the NAS, which is extremely limited. Now, it's not limited because nobody thought to design it. It's limited because it wasn't a driving requirement as these systems were designed year after year over 50 years. A good example of this, and I'll get to it later, is VHF voice. There's no security around VHF voice, but there is operationally, and I'll get to that. So the future CNS that we need to develop is one in which we have a shared use spectrum and a shared access spectrum. These will use LTE and 4G-like mechanisms. If we look at the overall technology of 4G and LTE right now, there are quite a number of spectrum slices that are being used very effectively and using mechanisms that allow many, many communications to be carried at the same time across small slices of those spectrums. So those LTE and 4G-like mechanisms will help us drive that future. Now, there is kind of a ongoing discussion about how do we possibly use the current cellular communication industry as part of that solution. And it very well could be a strong part of that solution, but we have to develop the overlapping domain solutions where if we're bringing a new aviation shared access, shared spectrum system, and we still want to use LTE, 4G, or 5G and into the future, we have to find ways for those to be completely interoperable, seamlessly, automatively, using cognitive radios and not having to worry about operators tripping over how things are being configured. Moving on with this future CNS, and we've heard it from other speakers, the advanced air mobility, urban air mobility vehicle demand is going to drive down size, weight, and power for our radios to a point where we have to combine radios into multi-use devices. That's for two reasons. One's weight, and the other is simple cost. We're now looking at developing vehicles that carry, we're flying taxis, flying buses, flying cars. They can't function in the NAS the same way using many radios and hundreds of pounds of weight. So we have to integrate these things in order for this entire thing to work effectively. The other parts we're going to carry into this, and it's a part that the Glenn Research Center is looking at very strongly, is satellite services, including developing LEO, low Earth orbit services, such as Starlink and others, into a fully integrated architecture. So those have to be pulled into this as well. Another piece that we're looking at is combining capabilities for single-use radios. And you can go back to cognitive, which a radio is swapping waveforms and developing different capabilities in small slices of time, where we might actually use radios as radars at the same time we're using them for ground communication. So that's kind of the future environment that we're looking at, where we're starting to pull all these pieces together, and we're carrying a longer plan of integration of capability across spectrum, across technology, and across our overall operating capabilities. Now, security will have to be designed into this from the beginning. So unlike what we have right now with the NAS, we have to develop the security models at an architectural level instead of looking at security as being an individual piece that we're applying to each part of our technology. So I want to go back to the VHF voice example for a minute. you can look at VHF voice as having no security, but in fact it does. And we've seen this in people trying to spoof towers at airports. The controllers and the pilots that are frequent to that airport know each other's voice and have been able to catch these things. So how do we replace this familiarity between humans in our overall security model? This is not just VHF voice, it's across the board. So that's a fundamental question that we need to answer in research. We also have to look at the entire security environment that's being developed today. There's a lot of work being done in ICAO with an overall trust model for the nation, for the world, and a global resilient aviation integration network that is working to solve some of these. We have to bring these services in, and we have to develop the new service capabilities that will enable this overall environment. So that's kind of this future CNS. There's a number of things we can do from a cooperation and coordination standpoint. You know, it's how do we leverage industry to do this? So first, we have to adopt a doctrine that capability and service delivery should be industry responsibility as much as possible. It's moving away from government providing to government helping to lead industry to provide. We have to begin to work with industry as soon as practical in these research efforts. I don't know where that is in the TRL stack for these things, but we have to bring them in as early as we possibly could. Standards development to enable this operability is going to be critical, and NASA already does that, and we're picking up more and more work in those slides. Then we have to identify and develop a strategy to break down these barriers, such as safety critical, and develop new models for security that are focused on safety. Security can eat your lunch if you spend all your time doing it. So we're looking strongly at the intersection between security and safety. Cyber safety, that cyber safety intersection is going to be the key point in developing our risk profiles so we know where to put our efforts. So thanks, appreciate it.
Thank you, Paul. So let me just turn for a quick question to Jennifer. So you heard the perspectives from the researcher side, right? So let's view this as capabilities to be brought to bear. So if you, as you're looking at your sector and all the folks that are essentially wanting access to this airspace and being able to conduct their missions of the future, what would you view as some of the biggest technical challenges or the key enablers that we need to address? Things that, for lack of a better word, that are maybe inhibiting, evolution or inhibiting innovation. So, I mean, if we were to say, if we were to break down 2 or 3 of the tallest issues, what do you think those should be that we could be looking at?
Yeah, well, I actually have a long laundry list, but I'll try to focus only on 2 or 3. So as I said earlier, we've spent all this time over all these years just getting to a moment of acceptance that we need to rely on communications resources and networks beyond aviation in order to satisfy all of these needs. Mm-hmm. But now we're at the prove it moment, right? And what the regulators need to see and what the aviation industry needs to see is that we can validate the use of these commercial networks in a manner that assures that there's interference-free operations and that it has the safety and the reliability that's really needed. I think that's something that FCC really needs to see. It's something the FAA really needs to see. We've worked on a set of metrics with the FAA for testing of use of these networks for this purpose. We need to see that data. They need to see that data in order to validate that we can, in fact, use these other resources. To Paul's point, 5G slicing or 4G slicing of the network in order to create an aviation slice that has an environment that's very predictable for aviation is something that also should be tested out. And maybe that's something that's necessary on a risk-based paradigm. I couldn't agree more that using cognitive radios and looking at shared spectrum resources and technologies is really essential here. So spectrum access systems that are otherwise used to protect federal operations and allow for commercial operations, that's something we really should be looking at incorporating into our UTM systems in order to be able to assign the right spectrum for any kind of unmanned aircraft mission, and to be able to switch between and among different spectrum resources depending upon the needs. And then I'll just touch on that last point that Paul made. I mean, this is such a great panel, by the way, just such great perspectives from everybody. The cybersecurity piece is really important. And, you know, the White House released a paper maybe 18 months ago now about what happens when we start to incorporate commercial networks into aviation, and what kind of risks does that pose. And so it's possible that we need some kind of an aviation protocol over the top of any of these resources that are used in order not only to ensure interoperability, but also the safety and security of, you know, the particular resources, but also the air traffic management system at large. So I think those are, I mean, I have many more, but those are probably the top few.
Okay, thank you, Jennifer. Really appreciate that. Let me ask one more question, and then I would like to turn to the audience. So just quickly turn to Badri. You know, you've heard everything from our rest of the panelists. Now, if I were to ask you, based on your experience, that everything you've done for SCAN, what do you think, or what are your perspectives on being able to leverage those capabilities towards this, you know, lack of a better word, atmospheric work, right? So you're, you know, to the suborbital application, that everything you've done beyond the orbital applications.
Yeah, thank you, Akbar. Definitely the environment I operate in is a little bit more complex from a protocol perspective, as we, you know, the propagation delay may get you here and there, and also the complexity of our operation when you have spacecraft going at the speed of 17,000 miles per hour, as compared to suborbital platforms that go, you know, like they seem like stationary. So definitely the suborbital asset to include all of the aviation needs can be supported from LEO, MEO, and GEO very easily, and as they dwell in their beam for quite some time, they don't have the challenge of, you know, going from beam to beam in a fast way, such that by the time you acquire, you are moving out of the beam. I saw and I heard, you know, pretty encouraging things from Paul, from PK, and also Jennifer, and everyone. And I see some utilization of our technology. The technology I'm investing in that will be demonstrated over the 2 to 3 to 4 years, from protocol that includes disruption tolerant networking, DTN, to the cognitive radio that we are going to demonstrate. And we have potentially a demonstration that will take place in a couple of years, flying satellite to ensure the safe operation of these cognitive capabilities. To the multilingual receiver, everyone talked about how we need to overcome these regulatory challenge. It's a must. We cannot be bounded by regulation anymore. You have to ride over those waves, and you have to do it in a very smart way. The technology is key. We can do it now. We are probably about 5 to 10 years behind, on applying the latest and greatest in technology. We have technology that's yet to find the application, the proper application. We are, putting the kind of roadmap that will enable us to use existing technology as well as future technology. We are already investing in quantum technology that will ride over some of the optical capability that we are building, provide more security and more assured access, and it can allow for many other applications that are not COM related, but also can benefit from the technology. So I believe many of the things that we have been doing can be shared, and we can build this partnership with the aeronautic community as a whole. Definitely the challenge is to get buy-in by the industry. When you are pushing for interoperability, you need to have willing partners. The industry, they very often they go after unique solution because that's where they can command control of a portion of the market. You are talking about the spectrum, although we are going to use the spectrum in a very smart way and allow for this, allow us the ability to reconfigure ourselves both in time and in frequency as well as in waveform, you know. But you definitely need to allow some time for the infusion of all of this technology, because we can develop all the technology we can, but you need to have some buy-in and a way to infuse it into operation. That's a very tricky thing, and you may not get that buy-in. In addition to the security aspect, Paul talked about the security. Yes, and Paul, good to see you again. But security is key as you are navigating from one platform to the other. How do you maintain the integrity for your service? Not only for your comm service, but also nav service too. nav service, because if you are to rely on GNSS services, they can be, you know, the integrity of that service can be compromised. How can you maintain the integrity of these services? So we established an office within SCAN. Just, I have a service integrity manager that's working just on that, and we are working with the PNT advisory board to target also security and like service level security for all navigation issues. Sorry about that. So that's probably I need to give time to other people. We are running out of time. But these are good topics, Akbar. And I appreciate this forum. And I see so many similar ideas. We are, it's just we need to put an effort to bring all of these ideas and to collaborate among ourselves. The budget is limited, but the willing, if we can get leverage the willingness of everybody to work together, we can go the extra mile.
Absolutely, absolutely. And that, and I want to jump on that last point. I will be in touch with you personally shortly on a lot of these topics.
Okay.
So just giving you a heads up already. So let me turn to Jim. I think we may have time for one or maybe two really quick questions. So depending on how the questions go. Jim, let's turn to audience questions.
Sure. Thanks a lot, Akbar. Yeah, we've got some time for a few audience questions here. But first, I just wanted to start off, thanking everybody for this. This is great. Really good to have everybody here. And I just wanted to say, I might be dating myself here, but cognitive radios. We've come a really long way from crystals. And if anybody ever flew RC, frequency clothespins at the flying field, that kind of thing. So we've come a really long way. And PK, for you, the folks from Case Western are listening. We definitely want to be back at Case Western or at Case Western in 2021. We hope we can support that. And they would be happy to have you and your daughter come by and say hi. So they just wanted me to pass that on for you.
Thank you.
So a question basically on international, aspects of all of this. And this is going back to more the space environment. What are the major challenges in international collaboration or cooperation when it comes to comms? And particularly when we go to the moon, and not just we US, but we lots of different nations, and potentially to Mars, are we looking at several separate systems, or are we looking at working together internationally to put together kind of one cohesive system that everybody can use? What does that look like?
And allow me to answer that. We definitely have a number of forums that we've established to look at interoperability among all space users in deep, near Earth and as well as deep space. We have something called the Interoperability Plenary. It's a representation at the AA's level and those who are responsible for comm capabilities across all space agencies that come together every now and then and decide on an agenda that's handled usually by the IOG, which is the Interoperability group, as well as the CCSDS, the standard group, as well as the SFCG, Space Frequency Coordination Group. And we also work with the GNSS community to establish an agenda such that we can have an interoperable set of capabilities that when needed, we can provide cross support to each other. For the moon, we put out a memo that designating, you know, and everyone, NASA has a good reputation and everyone follows our lead. So when we step in and provide leadership, people just, you know, work with us and afford us this role. We established a, you know, a spectrum manager for the moon, that anyone, including commercial entities, who want to go to the moon, they'll have to go by that, you know, spectrum manager. The same way for, you know, for comm capabilities as well as nav capabilities. We are, you know, by the end of August, we should have converged on a lunar architecture, and we'll be providing guidance to everyone, to all potential players, potential partners, and you know, to abide by, from standards to also to the, you know, to the utilization of frequencies. And believe it or not, even though even those who are not partners, because the potential for interference, everyone wants to maintain safe operation. They will look at what's going on and they try to coordinate with us. All space agencies, including China and others, they do coordinate through us on you know, utilization of spectrum resources in deep space. So we have established ourselves as a credible entity to manage and operate and coordinate all activities up there.
Okay, great. Looking at time, I think we may have time for one more quick question. Jim?
Yeah, and actually this one was directed at Paul. Are there preliminary strategies regarding automation of security measures that rely on people? You were talking about the VHF thing and pilots recognizing each other's voices. Is there any reliance on people in all of this? Were there, you know, merging with all the automation that we're talking about?
So no, there's not really preliminary strategies for being able to do that. We're looking at how things function today within a human-mediated environment, and then trying to translate that into how pieces would function interoperability from an interoperability point of view in a non-person environment. And we have to translate those, because one of the challenges we have is integrating with the current NASA as we push technology forward. So VHF is a good example of that. It's how do we start to look at replacing the VHF communication between pilot and tower with these new automated or even fully autonomous systems. The same capability has to be provided, but we also have to replace the security that's inherent in that human mediated part. So it's an open research question. We could look at kind of the fundamentals of what are available in terms of security protocols and lay them in there, but there's no guarantee that's going to work as effectively as we think they will. So. Okay.
All right, let me just now do a quick wrap-up lightning round question to all the panelists. So I would say in 5 words or less, describe what's keeping you up at night, and or, you know, what are you see that's just you know, keeping you excited. I'll start and I'll say, you know, this is the best time since Wright brothers and perhaps the jet age. Definitely exciting world, and I'm very excited for the future. Jennifer, what's your?
Yeah, what keeps me up at night is my concern that industry and the regulators are not coming together quickly enough on these comms issues. And that we have a lot of work to do and a lot of testing to prove out the concepts that we're all talking about here today. And that we do need to do a better job of collaborating on all of that.
Okay, thank you. Badri.
What keeps me awake at night are just the people and who have their own agenda that are not looking after the common good. You know, they are looking at their personal interest. We have the means to really solve any problem if people are willing to do it. It's that and unwillingness because of their hidden agenda that's really keeping me up at night. So,
okay. PK, 5 words or less, what's keeping you up at night?
Seamless, ubiquitous, continuous communication for all.
There you go. Okay, Paul, what's your quick keeping you up at night?
Making sure that cybersecurity is not going to limit our ability to actually do the research and development, keeping it as the minor player it should be.
All right. Well, what I would like to be able to do is, personally provide a virtual applause to all of our distinguished panel members here. And really want to thank, Jennifer, Badri, PK, Paul, for your presence today at this great symposium. As PK pointed out, it is named after our great American hero. And also to the organizers, we're looking forward to being able to actually do this in person and on site next year. And this has been a great opportunity for everybody, and really appreciate this this session, and also our panelists. Jim, over to you.